Pyramids come in various bases, but why do we call them regular? Learn the reason here in Mathematics of Engineering. Pyramids include different polygons for bases, but each side extends upwards, converging at a single vertex. The term regular describes the base of the pyramid. The base is a regular polygon. By regular polygon, we mean all sides are equal. Examples of regular pyramids are regular square pyramid, which means the base is a square. The second figure is a regular triangular pyramid, which has a triangular base. What are the parts of a regular pyramid? Down the bottom of the pyramid is the base. For this figure, the base is a square. Extended upwards are the lateral faces, and in the case of the example, there are 4 faces. Those are 1 from behind the figure, 2 still behind the figure, 3 in front, and 4 on this side. The total area of the triangles is known as the lateral area. This is the area protruding from the base. The area of the base also depends on the polygon provided. By taking the summation of the lateral area and the area of the base, we compute the surface area. Let's continue defining the other components of the pyramid. The sides of the polygon base are still gonna be tagged as sides S, where the points are also called vertices. However, the point of convergence of lateral faces will be what we label as apex or vertex of the pyramid. By dropping a line down from the apex to the center of the pyramid, we can find the altitude, or the height of the pyramid. The line from the apex to the center is called axis. Another line dropped from the apex and bisecting the side of the base also provides the slant height of the pyramid. This is denoted with a cursive L. The third line starts from the center of the base and bisects the side. This is called the apothem. Let me reiterate once more. Apothem comes from the center and bisects the side of the base. Check further that the 3 lines we created actually forms a right triangle, where the axis and apothem are the legs and the slant height is the hypotenuse. With so many polygons for bases, let's review the different equations of their areas. For a square base, with each side of the polygon labeled as side, the area is taken as the square of the side. A rectangular base has elements of length and width, so the area of a rectangle is the product of length and width. The third is a triangular base with components of base and vertical height. So the area of a triangle is half of base times height. How about for the multi-pointed polygon base, say a pentagon? The area of this pentagon can be solved by breaking it down into triangles. While the lines of the polygon are called sides, and the distance from the center to the vertices are radii, from the derivation where a circumscribing circle can be used. Also, the distance between the center to the perpendicular bisector of a side is the apothem. There are 2 ways of solving for the area of the base. First is the triangle method, which is basically counting how many triangles there are in the polygon, knowing how to compute for the area of a single triangle. So we can say the area of the polygon is the area of one triangle times the number of triangles comprising the base. The area of a triangle is half of base times height, and the number of triangles is denoted as n. From the figure, the base is also called side S, and the height is also labeled as apothem. So the area of the polygon is half of S times apothem multiplied by n. The other solution is the apothem method, which is basically derived from the triangle method. The pentagon has 5 sides, which we denoted earlier as S, with the number as n. But if we take the individual triangular areas, we can expand the area of the polygon as half of S times A, 5 times all over. If we extract half of A, we have 5 of S, which is basically the perimeter of the pentagon, denoted as P. So the area of the polygon is half of the apothem times the perimeter. Next is an example to show the procedure in looking for the lateral and surface areas and the volume of the pyramid as shown. First is to look for the lateral area, which is just the area of the protruding triangles. In this case, we have 5. Let's solve the lateral area through triangle method. The equation is half of the side length times the slant height and the number of the triangles. That is half of 8 times 10.6 by 5 triangles, which is simplified as 212 square feet. Through apothem method, the lateral area of the pyramid is half of the perimeter times the slant height. The perimeter is 5 times the side length of 8 feet, giving 40 feet. So the lateral area is then half of 40 times 10.6, also giving 212 square feet. Moving on to solve the surface area, or the total area of the pyramid. This is taken as the lateral area plus the area of the base. The base is a pentagon with side length of 8 feet, and the apothem is also given as 5.5 feet. The area can then also be solved through the two methods. With the triangle method, the area of the base is half of the side length times the apothem times the number of triangles. We got half of 8 times 5.5 times 5, giving 110 square feet. We should have the same area when using the apothem method, with the equation half of the perimeter times the apothem, where the perimeter is 5 times 8 or 50 feet. So the area of the base is half of 40 times 5.5, resulting to 110 square feet. The surface area is then solved as the lateral area plus the area of the base, which were just solved as 212 and 110 square feet. So the surface area is 322 square feet. For the pyramid's volume, we use the equation of a third of the area of the base times the altitude. We figured what the area of the base is, but we still need to look for the altitude. This is through the triangle composed of the slant height, the apothem, and the axis. The altitude or the height of the axis is solved through Pythagorean theorem, that is, the root of 10.6 squared less 5.5 squared, which results to 9.06 feet. With both volume parameters already known, we can solve for the volume, that is a third of 110 times 9.06, which gives 332.2 cubic feet. The next figure is a triangular pyramid with the given parameters of the slant height of 11.3, sides of 9 cm, and the bisector of the base with a length of 7.8 centimeters. First, we solve for the lateral area, which is basically the area of the triangles. By extracting a lateral face, there are the base of 9 cm and the height of the lateral face of 11.3 centimeters. The area of the triangle can be solved in two ways. The first is through triangle method with the equation of half of the side times the slant height by the number of the triangles. The lateral area is taken as half of 9 times 11.3 times 3 triangles, giving 152.55 square cm. This value should also spring out when we use the apothem method, with the equation half of the perimeter times the slant height, which turns out as half of 27 times 11.3, which indeed gives the same answer of 152.55 square centimeters. The surface area is the same as the total area of the pyramid, which includes the area of the base with base of 9 cm and height of 7.8 centimeters. Being a triangular base, the equation is half of base times height, that is, half of 9 times 7.8, giving 35.10 square centimeters. So the surface area, as the summation of the lateral area and the area of the base, is solved as 152.55 plus 35.10, giving 187.65 square cm. For the volume of the pyramid, we use the equation of a third of the area of the base times the altitude. With the area of the base just solved, we continue to determine the altitude using the triangle where the base is half of 7.8 and the hypotenuse is 11.3 cm. Through Pythagorean theorem, we take the altitude as the root of 11.3 squared minus 3.9 squared, giving 10.61 cm. We take a third of 35.10 times 10.61, which makes 124.137 cubic centimeters for the pyramid's volume.